readiness levels. Their measurement, maturity, as you can read. And the key point is they are a common language for technology development. It's a scale from 1 to 9, where the first 3 ranges are generally basic research laboratory applications. 4 and beyond is where we actually turn the new technology into something that is useful, applications, technology development. And as you can see, 5 and 6 levels are the prototype and research, and 8 or 9 are actually when we actually use them for space. And I asked, why are they important? And it said, as I said, a common language, common terms that we can use technology levels throughout the world. And they make a difference, especially for systems engineering. They give us a framework, how we evaluate innovations. This came about basically in NASA when they first were developing. They had different technologies, some worked, some did not work, and they did not know why, and they needed a way to evaluate the technology to see if it was ready for space, because if it was not quite ready, it can be quite disastrous on projects. I say one of the other reasons why they're important for innovation, as you know, everyone here in this audience is eventually going to be part of innovation. And there's 3 ways that you develop innovation, 3 key factors. You have to have a cluster of excellence. This World Space Conference is a gathering of people of excellence. They all have a common working knowledge and goals for space. The second is the networks of communication. These cluster of excellence, such as you, must communicate like we are doing now throughout the world with other people, other excellence. We're maintaining those networks of communication. That is what breeds ideas. And third, standards communication. These TRLs gives us that common language so we can all communicate that we're worldwide. We have one cluster of excellence can talk to the next cluster of excellence. And we have a common language. Now, getting to NASA is like a thermometer, various levels. You see, we have start the basic principles, technology concepts. We move up more and more as the development. We've gone from the lab. Now we're going into the technology demonstration. Finally, we're integrating the technology into space systems. And ultimately, it will be in space. I'll give a little history of it. NASA developed these space technology TRL levels in 1974. They defined them in 1978. John Mankins, who you may recall, he ran the ISDC in Los Angeles last year. That's the International Space Development Conference that was run by John Mankins. In 1995, he was a systems engineer for NASA, and he developed the TRL levels from expanded the definitions, and he added the TRL level 8 and 9. Before that, NASA never went beyond a 7 because their idea was just the prototype was good enough. And later on, 2003, the United States Department of County Office and the Department of Defense developed their own versions of TRLs. Also, in European Space Agency has their own version. So we see internationally all the TRL level schemes are very similar, and therefore we are now developing an international language of how to evaluate new technology. I'm going to elaborate the TRL levels one by one and go up. We see the first basic principles observed. Okay, basically, I say it's basic science. We know it's a basic, and the principles translated. And my example is I found a computer simulation of radiation in a low Earth orbit for satellites that showed how gallium aluminum oxide, gallium is a rare earth element, but aluminum oxide, showed it has superior shielding capabilities for electronics. That's very good that the electronics in space are subject to stray electrons and they will disrupt the electronics. It's called a single event upset, SEU, or a single lapse. Either way, electron hits the electronics and it changes them, and this is not good in space. Note that this particular study came out of a physics group in Mexico. Very international as our ways of operating. Now we move up TR level 2. We've taken those basic principles, but say, okay, can they be applied or identified? And we have applications, they're still speculative. We're just taking basic science and deciding, okay, how does this apply? My example of space radiation shielding is, okay, we've done the computer simulation. Now we actually would do some laboratory tests, determine how do the materials actually work. The computer says they should work well, but now we have to go ahead and decide how are they going to work. Do a little lab research. And then that moves us into our level 3. We're actually doing analytic experiments. We're in the lab. We're actively researching. We're doing studies, physical validation in the lab, proof of concept. And we're now taking, for my example, this gallium and aluminum oxide material in a lab and seeing does it actually shield the way we want to. So it would be the initial stage is does this actually work based on the science? And further, then you get in TR level 4. 4, we're moving in what I would call technology development. That's something serious. We've gone beyond the lab. We've now gone to we're actually doing actual components. That the basic elements of the invention are integrated. We say, can we make pieces work together? Can you validate? Does it actually work? Let's do some pads. Example would be a patch cord. We would take in a lab environment, just patch together electronic components, shield it with our gallium aluminum oxide, and actually try some radiation, see if it actually works. We went to our level 5 component. We call that the breadboard of validation in a relevant environment. And this we would actually do a little bit more than a lab. We actually would take our electronic component, we would try to simulate space. We put it in a vacuum chamber. We would expose it to a radiation source in the vacuum chamber. So we actually would use it as a space subsystem, try to get as close to the actual space environment as we can. And this is for space development, and then say we want to know if this technology actually is going to work. There are 5, and now we get I go backwards. TR level 6, system subsystem. That's where we actually are moving up. We're using a TRL, whatever we invented, we try to demonstrate. We'd actually do this in space. We'd actually take a experiment, perhaps put it on the International Space Station or perhaps a satellite, and do that with any technology, put it in the actual space environment. So we are going. So this is probably the big step, and I'll get later on. This is where it starts getting very expensive. Once we've done out of the lab, it's really low cost. As we get out of lab, it goes higher cost. Tier level, I'm going up to 7, the system prototype. And that's sniffer. That's where we've gone well beyond a 6. That's an actual device that works. In this case, we actually had a integrated circuit. It would actually be shielded, and we actually would put it on satellites and using it. So our level of risk for failure is quite low now. We've reduced the risk for failure. We've moved up the chances for success. Now, TR level 8, flight qualified, as we say in the space system, subsystems, that this is the end of our development. We're integrating technology. We're still looking out for other problems, but there's no critical problems with our new technology. And my example, again, to be used on some non-critical components we would put on a satellite, but if it failed, we wouldn't worry about it. But we put it on, we trust it, but not totally. So we're still working to develop the technology. And TR level 9, that's flight proven as a key. We believe in this technology. It's always going to work for us. And here it is. It's fully integrated. The systems, are standard in operations, and hopefully someday this new shielding material becomes so good it's routine. But this would be applied for any technology. It's so good it's routine, and we can trust it in space. Yeah. And I say NASA, a little bit to history here. NASA traditionally, we will at American NASA and the research will stop at TR level 6 because that is good enough for them, and they rely on the commercial industry usually to drive to their higher TRL levels. In America, we actually will develop technology and we'll give it away. NASA will develop it and they will license it to a company and let them do the commercialization. And I have some examples here at NASA techbriefs.com. You can find a lot of variety of technology that we've developed and ready to license out or actually give away. It's nice to see it. That's the key. You pay for the development for TR level 6 to 9. That NASA's done most of the work. I have an example of Bigelow, but it's a very good. That is actually on the International Space System now. What Bigelow had done is developed the expandable modules, and NASA actually developed the expandable modules up to a TR level 6. But Mr. Bigelow paid to develop all the money to develop from TR 6 to TR level 9. And currently there is a module on the International Space System using this expanded module, and it's been tested for a year or two now. So it's actually working. I would show the YouTube video. However, I'm afraid there's some restrictions, so I'm not quite sure I'd be allowed to do it, but I can leave you the link so you can all see it. And the final thing here is one point. This was actually from the European Space Agency, but made my point. You see the various TRL levels. What you see is the cost, is my pointer. And as you get beyond 6, 7, 8, the cost really, you're spending a lot of money. And the key is this one valley of death. That's a common term, as we spent so much money, but we haven't quite made it to a productive, technology. And that's where many of our technologies, they fail. They enter valley of death for spending so much money, but we do not have enough to develop commercially. So that's the affirmative valley of death. In my current job, we're trying to prevent that, and how we do it is we try to develop our requirements very early, because we think the earlier you understand what you're doing and where you're going, the better you will be able to avoid failure. So it's the early planning is a key for us. Okay, this is where I'm questions. Do I have questions, Avinash?
Yeah, from the audience, if anybody wants to ask any question, please come over here so that you can directly talk to him.
Yes, appreciate it.
You might want to take it off your video too, or your share.
Okay.
Yeah.
Okay. Very good.
Please. Yeah. Here is a question for you.
Sir.
Hello, sir. Namaskar. Myself, Master Anurag Mishra from Kishore Suryavanshi International School, Nashik, India. So my question is that how GDALO3 material is used for superior shielding, and how?
Okay, that gallium aluminum oxide, how it's used for shielding. Currently, they use an aluminum oxide material. And the theory is they use that and they surround the integrated circuits, and it stops the stray electrons. Our computer simulations have showed that this gallium aluminum oxide will actually have superior results, that you can actually make it lighter and thinner and save weight. So that is how it does it. And their simulation, simulated, in the computer, electrons hitting the material and the shielding stopping the electrons. Is that a satisfactory answer?
Is it a cheapest way?
Is it a what?
Is it a cheapest way?
It may not. We will have to determine it. Your gadolinium is a rare earth element, as we know. And those are, rare earth elements, not rare. They're very difficult to refine. But I know currently gallium aluminum oxide is being used in a thermal spray application as a thermal barrier because it has great thermal characteristics, and they're using that on various parts inside aircraft engines, for example.
And sir, next question. Sir, what are the common points included in DOD technology?
The common, I think, where we
Common
differ is
features.
okay. Like, what's the difference between our DoD technology and our NASA technology? Is that how I understand the question, right? I think where we differ is particularly we are looking more toward operational at various different fields, where we're not going in the space of our technology. We would actually be looking toward means that incorporate it in operations. And I know in my particular group, I work with a lot of technology to repair aircraft. And so my technology actually has commercial uses. So it's actually not really defense, it's really repair technology. And our success is, can we get it to TRL 7? Because we figured TRL 7, it can be sold as a commercial project to the airlines. So that's sort of the differences. But if you read through all of the TRL levels, they're very, very similar.
Okay, sir. Thank you.
You're welcome.
Yeah, we had met John Mankins at ISDC in Los Angeles.
Oh, yes. He's a good, he is the man that developed a lot of this.
Yeah.
Good evening, sir.
Good evening.
I'm Aditya Gagre, and I have a question that
Yes.
you told us about TRLs. And with the
Yes.
upcoming technology of quantum mechanics and artificial intelligence, at what TRL would you place or NASA's research place artificial intelligence, or specifically the use of artificial intelligence in space expeditions?
I won't say for NASA for sure, but it looks like there's slowly development. A lot of it is still TRL 3, that it's in the stage. But the fact is, from my experience, these TR levels, particularly with software, they can proceed quite rapidly. We've had a lot of projects that are TR level 5, but when we're done, they quickly go up to an 8. So with NASA, I can't speak for them, but what I know from my experience, that they may be at a 3, but it can go very, very quickly. That is the nature of software development, that once you get past that TR level 5, it proceeds to 8 or 9 very quickly.
Thank you, sir.
You're welcome.
Good evening, sir. I'm Geeta Badnere from Adarsh English Medium School, Pimpalgaon, Baswant, from India. My question is to you is, how do you found it about the technical readiness, or how do you get the clue about it?
How do I use the technical readiness? And I understand your question. How am I using the technical readiness levels?
No.
Is that no? Okay, let's say it again. I had a little bit of distortion in your voice here. What is your question? Could you repeat the question, please?
How do you found it about it? What do you search about it?
Do I search for the technical levels? Yeah. Believe what I do, how I do it. It is a lot of judgment in determining what is a technical readiness level. We try to make it simple. But what I do is I'm looking for initial readiness levels and trying to see where my project will go. Because right now, my current job, I have a lot of different technologies. As they said, I will go from thermal spray to sensors to electronics to new materials. Okay, have I answered the question, hopefully?
Okay, thank you.
Thank you.
Good evening, sir. My name is Snehal Jadhav from Adarsh English Medium School, India. Sir, my question is that, is this system, this technical readiness level, means TRL system, is better than the system CATS launched by NASA in January 2015?
I'm not sure on NASA's stuff. I compared this system to what NASA did in 2015, or I'm not sure on that. What was the second half of your question? Pardon me.
Is the TRL system better than the system CATS launched by NASA in January 2015?
The CAPS by NASA, I'm not familiar with NASA's 2015, unfortunately. Yes. So I can't authoritatively answer that question. I just know this system has been, TRL levels has been progressing for so many years. So, unfortunately. Hello.
Good evening, sir. My name is Kabir Donde from GEMS English Medium School, Nashik in India. I just want to ask that we are taking certain measures for protecting the earth from different asteroids, meteorites and other collisions. So is there some protecting system for the moon also like this?
Yes. There may be a system protecting the moon. I do not know. If I would evaluate our systems in terms of TRL levels, we have not actually done it. It's all been theory so far. I would call our TRL levels for protecting the Earth maybe a 3, but we've done very little or we've actually intercepted an asteroid. Till we do that, that will be the key. So our readiness for protecting the Earth is quite low at this time, but there's a lot of different technologies out there. Does that answer your question satisfactorily?
Sir, I want to ask one more question that
yes, sir.
In some million years, the Phobos moon of Mars is going to stretch out and become a ring around Mars. So is that going to happen with our moon also?
I can't say. I just not that familiar with Mars. I know it'll stretch out, but a million years from now, it's so many factors I just don't know. But maybe some smart people in your audience like you can figure it out for us. Thank you.
Thank you, sir.
Thank you.
Yeah. Thanks, David.
You're welcome. I very appreciate the questions. And
taking us from TR1 to TRL 6 and between 6 to 9, does it come under classified information?
No, not at all. In fact, everything I work, it's military, but it's industrial applications. And because I work with small business, they can sell it to you. There's no classification at all.
And what work is going on beyond level 9?
That's hard to say. Where I've heard NASA has talked about beyond level 9 be something that can be used on Earth and space, that it's universal. They're discussing if they need a level 10 or not. But.
Yeah. Because a lot of new research would be required for Mars settlement on Mars and Moon and deep space and all that. So all those things must be going on.
Right.
Yeah. Okay. So, David, thank you very much. You are so kind that you could spare your time and give a live presentation to our audience. Thank you very much and bye-bye.
Thank you. It's been a very good honor.
So once again, on behalf of Maratha Vidya Prasarak Samaj and Nashik India chapter, we offer our sincere thanks to Dr. Verghese for being here all the day and no, he left. So thank you so much, Dr. Verghese, and very deep thanks to Mr. David Shilly for sparing the time and gracing this day with his wonderful presentation and wonderful interaction with our students. We are also thankful to Dr. Prashant Devre sir, Honorable Sachin Dada Pingay sir, Mr. Avinash Shirode, Om Prakash Kulkarni sir, Vijay Baviskar, Professor N.S. Patil sir, Education Officer of Maratha Vidya Prasarak Samaj, the principals of various units and institutes of MVP, the Department of Computer Science for organizing this day, and the dear and lovely students for interacting and making the session very lively. So before going to end the program, let me tell you the schedule of tomorrow, 6th day's schedule. In the afternoon session, we'll have the guest speakers Shri Surinder Singh, Dr. Jasprit Singh and Shri Jatna. They are from Director ISRO Chandigarh. So in the afternoon, we will have 3 resource persons. And in the evening session, we have a wonderful online presentation. I think when I announce the topic, the online presentation, perhaps you will definitely turn to this auditorium with your curiosity. And the man who is going to present online is Bruce Mackenzie, and he's the founder of Mars Foundation USA. So perhaps you guys can understand how important this session will be. This will be followed by Dr. Jaspreet Singh's presentation, who is the head of MFD ISRO Chandigarh. So tomorrow's day will be a great academic feast to all of us. So with the permission of the chair, I declare that.
Yeah, tomorrow's online presentation would be on living on Mars. मंगळावरच्या वस्ती, मंगळावरची वस्ती कशी असेल, काय असेल याचा presentation असेल. And I have taken this mic only to announce, not for only tomorrow, but day after tomorrow, because every day we had programs in the afternoon for students and in the evening for students and general public. Day after tomorrow, that is on Wednesday, 10th of October, we will have only afternoon program. The evening program will not be there, so the prize distribution, valedictory and other things would be clubbed into the afternoon program. My sincere request to all the students who have participated in essay competition, poster competition and model competition, there will be a prize distribution for first 3 winners in each category for all the 3 competitions, and also there will be a valedictory session. Also, we will be distributing certificate of participation to all the students who have participated. So may not be that everyone would come on the stage and get it, but we'll give it to the school from which they have been representing. So a teacher who is in charge of that school and who has guided the students, he is requested to come and collect the certificates. So please note, even though in the program there is afternoon program and evening program for Wednesday, not for tomorrow, day after tomorrow. So there will be only afternoon session and there won't be any evening session. Please note. Yeah. And the selection committee, the judges, the panel of judges would be visiting IMRT Hall for judging the posters and models from 10 o'clock in the morning. So all the students who have participated in this poster and model competition, they are requested to be present there in IMRT Hall in front of their own poster or model to explain if any judge wants to have any further information or clarification from the participant. So you should be there from 9:45 in the morning tomorrow.
Now with this note, with the prior permission of the chair, let us declare the end of this session. Now I request all the audience to stand for the national anthem. May I request the technicians to play.
पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उत्कल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे